This video is going to discuss the fundamental theorem of calculus part 1 and discuss a particular case or a particular application of the theorem. Okay, so the statement of the theorem is that if f is continuous, then if we express a function g as the integral of a function, notice here that the variable of integration does not match the bound, but rather the function here, g, is a function of x, and x is in the bound. Okay, so it's a bound of the integral. Okay, so g is the antiderivative. What this tells us is that if I differentiate this function g, I actually just get f of x. So my bound goes directly into the function as a variable that I'm looking at. Okay, so, and then here this is a further explanation of where this comes from, and you can read that at your own leisure. Okay, so just as an example here, m of p is this function. Okay, notice that our variable, or our variable that we are integrating with respect to is t, but my function is actually p. So, but if I differentiate m of p according to the fundamental theorem of calculus part 1, the derivative is just the function that it was inside my integral, only with p's instead of every occurrence of t. So it'd be 3 secant squared of pi times p plus 2. Okay, so I actually didn't have to really differentiate at all. I didn't have to apply any rules of differentiation. I didn't have to find an antiderivative either. Okay, so that's a nice quick use of the fundamental theorem of calculus. Now, the only thing that I'll mention here is that in this explanation here, technically, if the bound was something other than p, let's say, for example, it was p squared, okay, I would actually have to multiply by the derivative of that by the chain rule. So it would be all of this times 2p. If, again, it was something other than p. Okay, right now, I don't have that. It would just be times 1. Okay, an application of this theorem is with the accumulation function. And so the accumulation function, if you accumulate something, you're increasing the amount over time. So it gives you the area under the graph from a fixed value to a variable bound x. Okay, and so this is, again, we have a function represented as the integral. Okay, so here we have p of x representing the number of bacteria at x hours. We want to determine the number of bacteria present after 6 hours, and then model the rate of change for the bacteria colony. Okay, so if I want to determine the number of bacteria present, okay, this is just p of x. So I actually, for this first part, I actually just want to say, okay, well, p, I want to find p of 6. Okay, so that would be the integral from 0 to 6, 2 over t minus sine of 4t, okay, all that dt. Okay, and now this is just calculation. Okay, let me erase this. I'm going to actually do the antiderivative quickly. This is 2 natural log of the opposite value of t, and then derivative sign is, or the antiderivative is cosine, and it would be negative cosine, but it'd be plus here, 4t all over 4, and then evaluated at 0 and 6. Okay, so evaluate natural log of 0, oh, that one doesn't exist. Okay, so this at 0, it's not going to exist, so we're just going to treat it as 0. And then if I now do the evaluation for 6, this is going to be 2 natural log of the opposite value of 6, which is positive, plus cosine, oops, let's go forward here. Okay, plus cosine of 24 over 4. And I'm going to leave my answer like that for right now, just because it's nice and exact. I can get a decimal, plug it in my calculator, get a number. That's fine. Okay, now I just need to make sure, so I finish the first part of the prompt, I need to be sure to finish the entire prompt and model the rate of change of the bacteria colony. So what this is looking for is P prime of x. Okay, well, for this, if I know P of x is equal to the integral from 0 to x of 2 over t minus sine of 4t dt, then that means by the fundamental theorem of calculus part 1 that P prime is just going to be 2 over x minus sine of 4x. Okay, and that's it. Okay, so quick application of the fundamental theorem of calculus. This would also be viewed as an accumulation function too, because it's a number of P itself would be viewed as an accumulation function simply because it describes the number of bacteria that have accumulated since time 0. Okay, that's actually something important to point out. A is some fixed value. It could be 0, it could be negative, it could be 22. Okay, some other value. So in this video we learned about the fundamental theorem of calculus part 1 and discussed the application of it, which is the accumulation function, and did a quick example of it.